has not yet happened, and I'll end that story there. Let's see how we're doing for time. Okay, and then I think we can sneak in one more here, which is studies suggest Jupiter could have 600 moons. So Jupiter could have something like 600 moons measuring at least 800 meters, so that's roughly half a mile in diameter, according to a team of Canadian astronomers. They will present the findings on September the 25th at the virtual Europlanet Science Congress of 2020. Most of the moons are wide, irregular, and in retrograde orbits. Over the past 20 years, astronomers have found dozens of small Jovian moons thanks to the advances of large digital cameras. Back in 2003, Scott Shepard, Carnegie Institution of Science, already estimated that the number of irregular moons larger than a kilometer would probably be around 100. Now, Edward Ashton, Matthew Bowdoin, and Brett Gladman, the University of British Columbia, Vancouver, have detected about 4 dozen possible new Jovian moons that are even smaller. But extrapolating from the sky area they have searched, about 1 square degree, they conclude that there could be some 600 of these tiny objects orbiting the giant planet. The team studied 60 archival 140-second exposures of a field close to Jupiter, all of them taken within a 3-hour period on September the 8th, 2010, with a 340-megapixel megaprime camera at the Canada-France-Hawaii telescope on Mauna Kea. The astronomers digitally combined the images in 126 different ways, one for every possible combination of speed and direction at which a potential Jovian moon might cross the sky, and this method revealed 52 objects down to magnitude 25.7. Corresponding to the diameters of some 800 meters. 7 of the brighter finds turned out to be known irregular satellites of Jupiter. The others are almost certainly retrograde Jovian moons, which orbit the planet in the direction opposite its rotation. A paper describing the results has been accepted for publication in the Planetary Science Journal. If this sensitive 1 square degree pencil beam search already yields 45 formerly unknown moons, the researchers estimate that the total number of satellites within this size range must be around 600. The current official number of Jovian moons is 79, and I'll stop there. So I think I'll stop that with the story, and then you also wanted me to do a what's in the sky, correct?
Very briefly, 2 to 3 minutes.
Okay. All right. So I will light up my favorite application for that. And this was actually this morning, so we don't get to see that anymore. That's old news. Pop into my favorites list. And there we go. So I'll start out with, this is the autumn sky. So we are, and the date I picked, by the way, for this sky is September the 25th, the Friday for astronomy at the beach. So I thought I would pick on that night, since it's probably a night that a lot of us will be observing. I realize we won't be in the park in person, but hopefully we can get out and have a look. So you can see actually quite a few of the moons are out. You can see Jupiter, Saturn, of course, the moon, Neptune. And for those of you diehards that still want to consider Pluto to be a major planet, you could be an even more niche diehard and declare that Ceres, planet Ceres, is still a planet. And of course, over here we have Mars. And oh, by the way, we're now claiming that Uranus is visible as a naked eye object, tiny little dim star-like thing, but you are supposed to be able to see that without actually having to use a telescope or binoculars. When we do the planetarium shows for autumn, typically the story centers around the story of Andromeda. So I thought I would just sort of start out and point out the major objects that we talk about, which is, first of all, up here, King Cepheus. Very up, you can see the zenith there. Cepheus there, he is the king. This is meant to be a throne with the top back of the throne facing forward. Cassiopeia, his queen, she is also on a throne. Her throne is sideways facing Cepheus. And of course, she is the one that makes the boast that her daughter, the lovely Princess Andromeda, is more beautiful than even the Nereids, who are attendants to the god Neptune. In Greek, it would be Poseidon. Poseidon doesn't think that's so cool, so he decides that instead of giving Cassiopeia and Cepheus a timeout, he is going to destroy their entire kingdom and wipe out everyone in it, which they do not like. So they consult the oracle to find out, is there a way that they might appease the gods and save the kingdom? And the oracle tells them that they can do this if they will sacrifice place their daughter Andromeda chained to the rocks, waiting to be devoured by Cetus, the sea monster, pictured down here near the horizon line. It's about this time that our hero Perseus gets involved in the story and flies in on the Pegasus, a winged horse, which is gifted to his father, who turns out to be Zeus, to save the Princess Andromeda. And he defeats the sea monster by showing the sea monster the head of the Medusa, a gorgon so ugly that anyone who looks upon her gaze will be turned to stone. And ends up destroying the sea monster. He falls to the bottom of the sea, and of course he gets to marry the lovely maiden Andromeda and live happily ever after. So those are the major constellations that we usually point out. There are, of course, lots of them coming into the southwest. We're seeing the end of the Milky Way as we get into the later autumn months. It will become more and more difficult to see. Even Jupiter is starting to set rather early. Coming up, however, is now the opposition for Mars. And if I just put this in motion, the date for the opposition of Mars is October the 13th. So we are less than a month away. You can see I've got the time here set for, I'll just stop it there. This is actually October the 14th, but you can see we're coming up into an alignment. We only get to see Mars about once every 26 months. So this is one of the best times to see it. And by the way, we happen to be, I think the opposition 2 years ago was a little bit closer, but this is actually pretty good. Mars is bigger than it usually does appear in telescopes most of the time. And in the coming years, it will tend to get smaller and smaller. So get it while it's good. So with that, I guess that's all I have to say on Mars. The one other thing that I did want to mention is, actually two other things I'll mention real quick, is the moon. This is the Thursday before Astronomy at the Beach, very, very close to Jupiter. And if I advance the date just one day, you will see that it's actually now very close to Saturn here. One kind of cool thing that I like to try and do is see if I can find shadow transits or Jovian moon transits. So it turns out on Saturday at Astronomy at the Beach, there is a shadow transit of Ganymede, and it comes across with the Great Red Spot. So let me just back this up just a little bit here. I want to say it starts at, it's going to be around 11 o'clock, I think. Okay.
Hey, Tim, can you
make
give
it more
me
like
information on
10:45
that so I can log that in some of those Astronomy at the Beach events?
Oh, yeah, absolutely. So
Ye-
I would say it starts at about 10:35, and I can send that on to you.
Yes, follow up with Bob during the break if you could on that.
Okay.
Let's,
and that's it. So we've got the shadow transit. That's all I've got for what's in the sky.
That's good. All right. Thank you, Tim. So if you're interested in putting your own spin on In the News or in the Sky, we should have Jeff McLeod on deck for this Thursday. Adrian Bradley coming back to us next month. And if you are interested in doing the news or the sky, let me or Dale Part know and we will get you on deck. Thank you, Tim.
All right. Thank you.
So let's go into the officers' reports. As president, glad you all came here tonight because this is one of the weeks that we're always delayed. Keep in mind the Macomb meeting is 3 short days away. It is this week. It is this Thursday. So we will be seeing you all very shortly. We've got a lot from the Astronomy at the Beach gang tonight, so I will be brief, but elections are coming up. If you are interested in being on the nominating committee to help us run the November elections, let the board know. We can have 1 to 3 people per the bylaws on the committee. If you are interested in standing for office, let the board know. You may feel embarrassed about if you're trying to challenge a sitting officer, but depending on who the officer is, they might thank you for it. So, just try to get all that. If you are interested in any of the above, let us know by the October Cranbrook meeting. And with that, I will hand things over to Dr. Dale Parton, our program chair. Unmute.
Sorry about that. Thanks, Diane. And just to reinforce everybody, Our next meeting is in 3 days. Okay, this Thursday, we have a very special speaker, Dr. Ryan McDonald, who's at Cornell University and associated with the SETI Institute. His topic will be revealing the nature of exoplanet atmospheres. We just heard Tim talk about a signature that could be due to life on Venus. So we're also looking for such signatures on exoplanets. Then our next meeting will be on Monday, October the 5th. The short presentation will be given by Ann Blackwell. She's a graduate student studying astronomy at the University of Michigan. And the title of her presentation is The Little Big Bangs. And the long presentation on October the 5th will be given by Dr. David Levy with the intriguing topic, a Lyrid meteor shower, getting thrown out of Dad's will, and a journey through the night sky. So I can't wait. So that's what's coming up soon. Diane? You're muted,
All right.
Diane.
All right. Thank you, Dale. And let's hand things over to Riyadh, our observatory chair.
Yeah, hello everyone. Thank you, Diane. I visited the observatory September 12th, so just a couple of days ago. Everything seems to be fine. Both buildings are okay, equipment is okay. So, and as it has been the case most of this year, unfortunately, of course, the observatory, the buildings are still closed. So we're not going to have any open houses in person. We continue to have the virtual open houses, thanks to Doug and everybody else who's been helping with that. Yeah, it will remain closed until, of course, further notice once we figure out when is the safest time to get back to do some observing in person. Nothing else really at this time. That's it.
All right. Thank you, Riyadh. And Glenn, our secretary. Glenn, your mute's on.
Okay, I'll start over. All the meetings have been published. That includes the Cranbrook officer meetings and the general meeting, and also the Macomb general meeting. So they can be read in the current WASP. That's it for now.
Thank you, Glenn. Treasury, we've got Mark.
Thanks, Diane. So Treasurer's report, we have 90 current dues paying members. We've taken in so far this year $1,965. We've spent $510. And we have a total in the bank of about $22,968, so almost $23,000. All the details are in the WASP.
Very good. And Bob.
Hi, everyone. I have posted the Astronomy at the Beach link in chat. I would like everyone in the club to share that with everyone you know, your friends, your family, your pastors, your dog, everyone. We want to get a lot of people at this. The schedule for Astronomy at the Beach is astounding. I am very pleased with it, and I've been pounding on the website even today. So one of the things that I've done on the Astronomy at the Beach website is put a link in there so that the public can request speaker. I know our club and a lot of the other clubs have people which will redo their presentation or other presentations online, and we already got one bite. Ken Burton volunteered to handle that, so I don't know what's the status on that yet, but I hope we don't start getting inundated with these because we're going to do something if we do. Other than that, I've only got a couple reports of people doing stuff. Both of them is Dale Parton. He did an outreach event, and he's going to be interviewed by Astronomy at the Beach, so that ought to be cool. Other than that, share the Astronomy at the Beach event. So that's it.
All right, and in the interest of sharing the Astronomy at the Beach event, since the Saturday night falls on our open house night, our open house will be day 2 of Astronomy at the Beach. So we are not having a separate, we're just redirecting everybody to join the Astronomy at the Beach festivities and bask in it because they have put together a phenomenal slate of events. I am super excited at what we've got in store for y'all this year. And with that, I will hand things over to Jonathan, Publications.
WASP is up through very little effort of mine.
And I believe you have a theme for next week, right, Jonathan? Next month, rather.
Yes, so next month, as Tim mentioned, we're going to have the best Mars opposition for quite some time to come. And so we're especially seeking out any kind of Mars writing that you would like to do, or any pictures or drawings or cartoons, anything Mars related, we would love to have. So get your Marvin the Martian impression in gear.
Excellent. We'll have a special movie review for y'all, even if I end up absolutely despising the movie in question. Long story. Anyway, so we've got special interest groups. Solar Marty, I don't think is on the line. I've got some images from Soho that I was just going to throw the link in the chat unless somebody wants to share their screen. Not a lot going on right now in the Sun Gang.
I've got that right now too.
Thought you would, Ken. Throw it on up there if you could. Thank you.
Okay, let me do a share.
Riyadh runs our hands-on group. Hands-on is suspended for, basically if you want to do hands-on astronomy, you're on your own right now. History group, Dale Teamy is available. So Dale, have you got anything for us? That's a boring looking sun, Ken.
Well, I'm going to show you how boring it is, actually. There's actually another thing here.
Yeah, I looked at it the other wavelengths of light, and there wasn't much going on there either. Yeah.
Look at this magnetic sphere. Nothing.
Yeah.
Oh, wait a minute. That was it's really quiet.
It's a cue ball.
That is really quiet, and we're not even getting much. Not even getting much flaring either. I hate when it does that, but it.
All right.
It's like the sun died.
I was gonna say, now that we've pronounced the sun dead, let's talk about history. Because it's dead.
Okay, I'm stopping the sharing. You don't need to see it anymore. It's enough.
The stories of history's demise is highly exaggerated.
Yeah, it's so quiet you can walk on it. By the way, I did want to mention something. The 600 moons that are going around Jupiter, they could be artificial satellites by the Jupiterians launching them, of course.
And if there is an Elon Musk equivalent from Jupiter,
I was just going to say.
bad things are going to happen. All right.
They're a few thousand satellites short, though, if they want to get them off.
Good Lord. Dale Teamy, anything else for us?
Well, I've been digging into some of the books I got from Jonathan that were donated to our library, and there's some interesting stuff there. I'm ready to put in for the Armchair Astronomer series, but history so far is on hiatus, nothing to scan at the moment. And that's not it.
All right, I guess we need to get y'all some more stuff to scan, eh? So,
for sure.
Next special interest group in the queue, Astrophotography. Is Bill on the line, or is he up doing astrophotography? Bill Beers. Going once. Going twice. Okay.
He's got better things to do.
Yeah, like astrophotography. Next to the queue is Glack. Bob, you've said your piece on Glack. Anything you want to add before I let Adrian have his say? Adrian, Glack president, anything you'd like to add?
Yeah, Bob's pretty much covered it. Between him, Brian Odom, Jeff Kopmanis, they've done a phenomenal job with getting the website going. My job is basically then to just listen and give suggestions here and there. You all should give Bob Trimbley a hand, because without him, the 4 speakers that we have would not have happened. His connection, my dear friend Dr. Levy, who you'll be giving a poetry, I think a poetry talk, David, at the event. So if anything, and he's kicking off the event with that talk. So Bob said it already. Definitely come out. Tim, you've got a presentation. I've got a presentation on Stellarium. I think, Jim, you've got one. Ken, a lot of us are, when you say a lot of us in the WAS are participating, my lowbrow side is jealous, but then again, half of us are on the board. You all are the meat behind this thing, so we greatly appreciate you. And that's it.
Thank you, Adrian. Your leadership during this crisis has been greatly appreciated too. As a former GLAC president, I don't envy the mess that you had to get through, but y'all are doing a fantastic job. All right,
Yep.
last special interest group, Jonathan, Astro League, merch, and what remains of the library.
So the new issue of the Reflector is out, and we got our copy. If you think you're signed up for the Astro League and haven't gotten a copy, let me know. And I'm trying to get back in their good graces. So we'll hopefully be back in touch with them soon.
Okay.
And merch is there if you really, if you'd like me to mail something, we can do our part together to help the post office.
All right, it is 8:05. We have a lengthy presentation tonight. The short and the long talk are being combined into one deal, so we've only got 10 minutes. We'll be taking our break at 8:15. Do we have observing reports? Now the sky
I think I
conditions
see
have-
the effect of haze. That's my observing report.
Yeah.
Last chance to taste the Milky Way, and I hope I have something to shoot at.
We've seen many reports coming in on our Facebook feed about the smoke from the western wildfires catching up with Michigan, so that is definitely an issue right now. Any observing reports from before the smoke hit the fan?
Diane, I got a photo I could share real quick.
Sounds good. Let's see it, Mark.
Okay. So a couple weeks back, didn't send out an alert, but we had a nice conjunction of Mars and the Moon. They were about half a degree apart. So I was able to. Can you see my screen?
I can.
Yeah, I was able to capture a Moon Mars cell phone shot. Turned out pretty decent, but that was really nice because I discovered it somewhat serendipitously looking at planetarium software, but it would turn out to be a clear night, which is nice for Michigan.
Yeah, Jonathan and I saw that conjunction and a near conjunction the night before from Lake Huron up in the Sunrise side. And I don't think it was the early front of the wildfire smoke, but the horizon was orange. And so the gibbous moon looked like a partially eclipsed sun. It was so intensely orange, it was the same color as Mars. Unfortunately, we were not able to get any pictures to do that justice, but it was one of the most stunning pieces of visual planetary observing I've witnessed in a while. Anything else? Anybody getting good looks at Mars? I mean, it's nice. It's not quite in opposition yet, but it's good. David Levy's hand is up. David, take it away. David, you're on mute. Let's see if we can fix that.
I'm sorry about my muting, just having to discover where the mute button is flying off to. But we've actually had haze from the fires up in California and Oregon and Washington, so very thick that the only thing in the entire sky was Mars, and that was very, very dim. But Mars has been really gorgeous, coming out again here now as the smoke begins to dissipate. And also there was an Edda Draconid meteor a couple of nights ago. the second magnitude one. I wouldn't normally report it, but I love meteors. And that's kind of what I've been up to lately. Thanks.
Thank you, David. Under the horrific atmospheric circumstances, I believe these would be the conditions under which one could observe sunspots without aid. However, as we've established, there are no sunspots to look at. So, anybody see any sunspots through the haze?
No. None.
Afraid of that.
I do have
Yes.
a photo to share that I took earlier, just really quick. It's what the sky looks like with the haze in it. I thought it was really weird,
yeah,
so I took a quick iPhone shot of it, and I'll share. I think I have it in Lightroom. This is the picture.
Oh, wow.
I ended up catching a flock of geese in flight going by it. It's not often you catch the disk of the sun. Now that's an artifact from shooting at the sun with the iPhone, but it's not often you catch the sun, the disk of it, using an iPhone. And you can see how hazy. I mean, these clouds, it's supposed to be a lot bluer sky than this. This kind of took me aback because these are the clouds, and then you've got all of this haze around it. So we'll see how this progresses, but it's worse than the Canadian fires that I remember from a year or so ago. So
ironically we got skunked out of the last Mars opposition by a dust storm on Mars, and now it looks like we might get skunked by smoke here on Earth.
Yeah, I'd be lying if I said that hadn't occurred to me and I was kicking myself. It's not just the last opposition. The last two Mars oppositions had dust storm issues going on. So,
I have a couple quick pictures to show.
Excellent. Let's see them, John.
John, it looks like you're in a different...
I clicked on
like
share screen. Does this work? Oh, can you see my screen?
Yes, I can.
Okay, so what you can see is my picture of the moon and Mars and the position I had to get in my apartment and to be able to see them without going outside.
Dedication. That's great.
I got something, Diane.
Yes.
So I'm up north of Port Sanilac. I was here a couple weeks ago, and mine's naked eye viewing. I went crazy when I saw the skies here. And last night, I don't have any pictures or anything. All I can say is between like 3 and 4:30, I very much enjoyed sitting on the shore and seeing the meteors, nice, slow, long ones. And I also had the wonderful privilege of seeing the moon rise with Venus and seeing the edge on the moon completely. And it was seeing the glow of a cloud before it actually started to come up. So it was a really wonderful take-in of things I love most, being along the waves and this beautiful, beautiful evening with the rise of the moon and Venus. And that's all I have to say, but I wanted to share it.
That's beautiful, Therese. Yeah. No, it's we haven't always had the best conditions up there at Lake Huron, but they've certainly been poetic conditions, even when they haven't been astronomically appropriate. Has anybody had any final glimpses of Comet Neowise? We had a few people that were still tracking it last Cranbrook meeting. Anybody seeing it now? I made an attempt with 15 by 70 binoculars and no dice after the Cranbrook meeting last month. Nope, no Neowise? Okay.
Nope. I took my final picture when it was small, but you could still barely see the tail. So that's, I think, 2 months ago. I bid it adieu after that.
Well, we have, Ken, you've got something?
I have a picture from a friend of mine who lives in Oregon that I think you should get a kick out of. Give me a second here.
Get a kick out of, be terrified by.
Or cry.
Wait till you see this. Hold on a second. Let me get back. Let me get to you.
Hmm.
I'm going to take it. There it is. Take a look at this. I think that John is in the way. There it is. You got it? This is
Yeah.
this is a picture from Portland, actually. How's that? Right now. Look at that sky.
Yeah, better wear your mask.
I have a friend in the San Francisco Bay Area, and the sky was insanely red. It was I couldn't believe how bad it was. He said at one point it was hard to see down the block.
Yeah, my whole family on my mom's side lives there in the Bay Area in Sacramento. They've had ash raining down in their yards. They've had a lingering stench in the air that, basically, even if it weren't a COVID-19 thing going on, they'd be wanting to wear a mask outside because the air is just so disgusting. Today, finally, my aunt in San Jose reported things were a little bit better. Not normal, but noticeably better, and the sky bluer than the previous day. So, yeah, it's bad. And on that horribly depressing note, it is 8:14. Y'all can take a 15-minute bio break, snack break, BYOB fiesta, and we will reconvene at 8:30 on the nose for Jim Schedlowski and the feature extravaganza. See y'all soon.
Jonathan, have you got any numbers on attendees for me?
All right, we have 20 on the YouTube and 30 on here, so for a total of 50 right now.
Okay. John, my system went down. I had to reboot right in the middle of my talk, and I didn't hear the outcome of the beg letters. Could at some point I get updated on what happened while it's gone?
Oh.
Doesn't have to be now, but maybe by email.
Just about who was gonna, I guess that's not when I had, I had a connection problem too. It wasn't so much a connection problem as I think my virtual background screwed up something, but we dropped the YouTube and everything. So I don't know that we had a volunteer, but I mean, Diane and I have a lot of, we already do a lot of storage. So if you need somebody to hold on to things until the banquet or virtual banquet, let us know.
Definitely do. I need to have an address to put in the letter, and then I'll go ahead and start publishing it.
Sounds good.
Thanks, John.
I'll send you yours unless somebody else volunteered and I didn't hear it.
Will they hold at the PO box?
The problem is I don't know if the PO box is big enough for all items that they might send. If they send a lot of documents, I understand that box is not very big.
It's very small, but I don't know what their policy is if they'll actually hold. Well, sometimes I think they'll put a slip in there that there's a package that you can pick up.
Yeah. Probably better to use a home address.
Yeah.
All right, I'll await your input, John.
All right, sounds good.
It's good to see everybody here.
It's really great to have everybody here.
Nice to be seen, even though my picture's not there.
Yeah, my picture's not here either, but I can see most of you. This is actually a pretty good way to do a meeting.
Certainly accessible.
Yeah. I do have a poem to read if anyone's interested.
Absolutely, always.
I'm ready.
Okay. This is one that I wrote a couple of nights ago when I couldn't sleep, and it's actually done to the tune of a very famous Canadian composer who is buried right now approximately 100 feet away from where my mom is buried. And the title is Cosmic Variations on a Theme by Leonard Cohen. It's time to go outdoors tonight. The sky is dark. Some stars are bright. The Milky Way shines overhead. Now see a comet rises in the east. With end to strife, it brings us peace and calls us to a cosmic hallelujah. 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 Hallelujah.
Love it.
Now, where have I heard something similar to that before? I can't think or place the song. Jim, was there something? Does that sound familiar to you, Jim? Something about a Russian cosmonaut or something, if I remember.
Yeah, Sergei Korolev.
Yeah, Korolev.
Yeah.
So, David, there's Leonard Cohen's final album, which was, I believe, not his posthumous album is not so good, but his last album while he was alive was, yes, one of my favorites. And I was going to say, You Want It Darker is a very appropriate album title for astronomers. So
it absolutely is. And one of the things I like about You Want It Darker is that he used, for one of the songs, he used the choir from our congregation in Montreal, the Shar Shemayim. The interesting thing about Leonard Cohen and me is that he beat me by about 10 years to everything. He went to my elementary school 10 years before I did. He went to my high school before I did. He went to McGill, and he was a member of our synagogue. All of this approximately 10 years before my time. But when I first started falling in love with his music when he did Suzanne, but when he came out with Hallelujah, I was just sold. I think that's one of possibly the finest song I've ever heard.
I think, do I recall correctly that his father was the rabbi of that congregation, or I mean,
either his father or his grandfather was one of the founders of the Shar Shemayim, Lion Cohen and Lazarus Cohen. One was the father, one was his grandfather, and there are plaques inside the synagogue honoring both of them.
David.
Yeah.
Shana Tova.
Shana Tova to you too, Kenneth. And to all of those here who are about to celebrate the High Holy Days, Happy New Year, and may you all be inscribed in the Book of Life for a happy and healthy and COVID-free year.
We carry it forward to 2021 as well, David.
Thank you. If it's clear Wednesday, I'm going out observing at a dark site, so I'm really looking forward to that.
And I pray that smoke clears enough for that dark site to be worth it. I guess if things are getting better, maybe they're starting to get it under control.
Well, the wind here is starting to blow in a different direction too, so we may be in luck.
Oh, that's good.
Thanks, Adrian.
That's good. Yeah, I guess it's ironic that I picked for my virtual background a reddish sky of behind the Golden Gate Bridge.
Yeah, I see it.
There was nothing going on. And so I guess it's sad if this is how it looks in the daytime now. That's probably not good. But yeah, that was a night picture, and I purposely messed with the sliders, and there are a couple of stars behind it, and it has this violet look. So I thought it was pretty cool.
I remember visiting San Francisco years ago and walking across that bridge. Just an incredible structure to walk across. It takes a couple of hours, but it's worth it.
Yeah. I went one way to Sausalito. I stayed there till night, started to walk back across, and security came and helped me get off of the bridge a little bit faster, but not without telling me about the story surrounding the building of the bridge and why it was originally built. Everything that I pretty much wanted to know. So it was a wonderful trip, and I have several pictures of just the Golden Gate Bridge itself.
Yeah. So do I. Anyway, Adrian, I wish that you and the others could come observing with me Wednesday, but really looking forward to it.
When I get my transmitter, my beamer safely working, I would do that. I'd just go, let's go, and we'd be there. Perhaps one day.
Guys, see the black hole thing up here?
It's pretty good / bad. It's hard for a black hole.
Yeah, it is.
I love the guy walks into a bar, stand up.
Everybody's getting pulled into the black hole. That's my golf game, by the way.
That's priceless, isn't it?
Isn't that great? I love that stuff. Heck, a little chuckle for everybody. There you go. Hi, Cliff. How you doing, Cliff? You're muted.
Unmute, Cliff.
Almost there.
Unmute. Come on.
There you are.
Okay.
There you are. How you doing there, kiddo?
Yeah, quite good. Still doing the planetarium stuff and working with a project with NASA. Our planetarium was the only one picked for this project for the 30th anniversary of the Hubble Space Telescope. It was supposed to take place on the 24th of April.
Oh, my.
But they didn't get their banners out. And we're going to have to do our open house virtually whenever that is. We don't know yet. That's it. It's been taking up my time.
All right. That sounds.
I was supposed to do a presentation on that anniversary of the Hubble. That never happened.
Oh,
Tim, that was a great in the news segment you did.
Oh, thanks.
Hey, Cliff, when you get finalized information on that, send it to me.
Yes. Oh, yeah, we'll definitely let you know, but I can't get a firm date. The planetarium's closed. Period. It's attached to an elementary school, so they're not going to let me have anybody come to the planetarium now.
Well, even so, some of the colleges that are opening only for essential classes only, no extracurricular activities, no meetings, no nothing. So the planetarium I normally do presentations at is closed. They said, regardless of what you hear about classes, the planetarium is closed.
Yeah, but Big Ten football is going to be open in about a month, from what I hear.
What's going to be open in a month?
What's that? Question came in?
Yeah, I was asking what's going to be open in a month?
What's going to be
Big
open?
Ten football.
Big Ten.
They've been fighting to reinstate college football in the Big Ten, and I think they've gotten somewhere. So you may be seeing a few games in October.
Better than watching the Lions.
So, and maybe that's the driving force behind it.
Could be.
Because we'd rather play in an empty stadium and give ourselves a chance. I will say Major League Baseball seems to be handling, after a rocky start, Major League Baseball seems to be moving along pretty well. Either that or they're disguising COVID-19 as tendonitis in the shoulder or some other injury. I'd like to hope that they're not. But we're seeing it under control there in baseball. Basketball, I haven't really followed as much. And in NFL football, where it remains to be seen how that's going to work. But testing every 3 days or more and very restricted can't go home, can't see anybody. They basically said if you want to play, this is it. This is life for the 8, 9, or 10 weeks that you're doing it. So athletes agree.
Yeah, I think we just found our Martian astronauts.
Bob, I did mail you the data on the shadow transit. I don't know if you saw the note.
All right, if y'all can hear me, start filtering back to your virtual seats, everybody. Got another minute or so to settle in before we call the meeting back to order.
Yeah, Tim, I did see that. And here I was nodding at the screen, and my camera was off and muted. So yeah, I got that.
Coming back.
Okie dokie, bottom of the hour, 8:30 p.m. Like to call this meeting back to order. Hope y'all had a good snack break or had some lively conversation going on. And I will now turn things over, as is customary, to Program Chair, First Vice President Parton, to introduce the night's speaker. Take it away.
Okay, thank you, Diane. It's my pleasure tonight to introduce longtime club member Jim Schedlowski. Anyone who's been in the club very, very long knows him quite well. He enjoys observing a lot and sharing that interest with lots of other people. In recent years, his passion for astronomical history and technology has become a big thing for him. He's not only a member of the Warren Club, but also the McMath Hulbert Astronomical Society. And he's also visited quite a number of major observatories. Spends a winter in Mesa, Arizona. Lucky guy. And perhaps the dark skies he enjoys there helped inspire his topic tonight, discovering the dark universe. Jim, unmute yourself and take it away.
Okie doke. Am I coming across?
Yes.
Okie doke. Let me find my the right screen here. Jonathan, can you help me?
Looks like
Yeah,
you have it under control.
Yeah, you're starting to
Okay.
share content, Jim. You're good. Just have it in the right mode and we're all set.
I can't seem to get it to show you guys the slides though, and let me read it. We went through this before, I think, once, Jonathan. Can you help?
Do you
Yeah.
have full screens, Jim?
I don't have a second. Got mine on extended, and that should do the job, but it's not letting me do that.
Well, it won't let you play the thing? Doesn't it let you play?
There we go. Are you guys seeing the slide now?
We're seeing the slide, but we're seeing that your writing also, but
Yeah,
you should have a separate place where only it shows them one thing.
That's the screen. That's the screen I need, but I want you guys to see the slide.
Right.
So
But
how
it
do I
should
do
give
that?
should give you a choice at the top
There should be a swap displays.
that says displays.
Yeah, but again, there's only one screen, so it's
Yeah, but
I don't think you can show both.
Yes, you can.
Yeah, I can. Done it before. I just
There you are. You just did it. I think that's it.
Uh,
I think
it's
you're
trying
there.
to get me to sign into Zoom here, and I don't want to do that.
Yeah, don't do that.
Do that.
Yeah, I think that's the wrong direction. It sounds
So-
like you choose to display the application itself.
I guess I'm still in the meeting, but I can't seem to.
And you get to, is there a play point that says at the top, this is a PowerPoint, right?
Yes, it is.
Then you should go at the top where it says play on your screen where you can see the whole thing, and it should put up the first one. And then as you move along, it'll move to the next one.
I'm seeing.
I can see it.
I'm seeing that something says you're sharing Microsoft PowerPoint,
Oh my.
but apparently I'm not sharing it. Let's see.
You're
Well,
you're sharing what's called the presenter view.
Good view, right?
Yeah.
And I need the presenter view myself,
Right.
but I need to share the slides with you guys. Like
But
that.
again, that should do that. There you go. I think you got it.
Well, not.
Okay.
Looks
Well,
Are
like
you
you,
seeing
yeah, you're
this?
good. Now you got it.
You got.
Can
The,
you
yeah, but
see
now
it?
Jim,
looks
Jim
good.
can't see the presenter view, right?
oh, I've got the presenter view.
Okay,
Go.
perfect.
Go,
Then we're
Jim.
good.
Set.
All
Let's
right.
go right here.
I think we're okay, right?
Yeah.
Okay, it works.
You the man.
Okay.
All right.
All right.
All
Let's go. sorry about the delay, gang.
Somebody's going to have to teach me how to do that.
Yep. You guys you're ready for this?
Yep.
Good evening, ladies and gentlemen. Welcome to the 12th anniversary of a September evening at Cranbrook with Schedlowski, this year virtually. For this year's presentation, I picked up a theme that I covered some 9 years ago from this same podium. Just a second, you guys have got a little thumbnail up here that I've got to get rid of now, which is in my text. How do I do that? Huh.
Oh, it's not showing up for us. Oh, I see.
Well,
Just drag it out of the way, I think.
Yeah, okay. I gotta get rid of you now, Jonathan. Okay. You've got a little host screen there. Maybe I can work around you, I guess. Here we go, I think.
Just shove me off the screen if you can.
I gotcha. I picked for this year's presentation, I picked up on a theme that I covered some 9 years ago from this same but non-virtual podium. The title of my 2011 presentation was, quote, "The Way We Found the Universe," and it covered that exciting period from the early 1900s when Einstein and Hubble revolutionized our understanding of the universe and, helped out by the likes of Henrietta Leavitt, Gustav Schleifer, George Lemaitre, and others, formulated the, at that time, revolutionary Big Bang theory of an expanding universe with its island galaxies. This year's topic came to my attention last May when at the tiny library in Roscommon, Michigan, where my wife and I hang out, I found this slim volume, which is not changing the screen here, found a volume which caught with this statement in its introduction, quote, "Most of the articles gathered in this anthology were selected to capture the revolution that has shaken cosmology and our understanding of the universe in the last few years," end of quote. So with a statement like that and my cursory awareness of such things as dark matter and dark energy, my curiosity was aroused. This book's compilation of articles by noted astronomers and physicists essentially provided a primer on the controversies that have been going on for the last few decades, the most momentous since the proposal of the Big Bang Theory in the 1920s and 30s. So after perusing a few other subjects, including one appropriately titled, quote, "We Have No Idea," end of quote, and being cautioned by Dr. Parton last summer that this would be a risky presentation topic, I decided to proceed with researching what has become for me a fascinating ongoing chapter in the history of science. I hope you'll enjoy my attempt to summarize for you the current turmoil going on in our understanding of the universe. In searching for an appropriate title, I was tempted by numerous in various publications and by the title of a conference that I attended at the Arizona State University's Stewart Observatory in Tucson last January, which imply a crisis, turmoil, or tension within the cosmology community. I finally settled on the less dramatic phrase above, which suggests that much of this controversy has been brought about by the largely unfulfilled quest for the nature and properties of two mysterious quantities which have been aptly named dark matter and dark energy. My presentation then will review the standard model of cosmology, sometimes called the concordance cosmological model or the lambda cold dark matter model, and recently revolutionary revisionary thinkings regarding it. Let us first look at the general structure of the universe as it is now defined or described by the standard model of cosmology. It is some 13.8 billion years old. Its observable diameter spans 93 billion light years. It contains over 10 million galaxies, each with from 10 million to 1 trillion stars. That's 10 to the 24 stars, or more than all the grains of sand on Earth, which are organized into clusters and finally superclusters, the largest gravity-controlled structures in the universe. Of the overall content of the universe, only 4.9% is ordinary or baronic matter, which we can detect directly, with the rest consisting of 26.8% dark matter and 68.3% dark energy, both of which we know very little about and which we will explore later. Since this standard model has been developed over the years with certain assumptions and theories and then validated with ongoing observations and data, I'd now like to review the history of our understanding of the universe as it has developed over the centuries in the Western world, from the early Greek philosophers through Copernicus, Galileo, Newton, Herschel, Hale, Einstein, and Hubble, and finally to today. The earliest models of the universe came from the ancient Greek philosophers and then later the Arabian astronomers, and are represented by Ptolemy's model of the universe, which were preserved in his book, the Almagest, which presented the Earth as the center of the universe with a sphere of fixed stars at a distance of 20,000 that of the Earth radius. This book was the authoritative text on astronomy for hundreds of years, and it was almost universally accepted until the scientific revolution of the 16th and 17th century. The Copernican sun-centered model eventually took its place, with additional contribution from the likes of Galileo, Kepler, and finally Isaac Newton, who with his mathematical treatment of the laws of motion and gravity finally allowed a somewhat modern perspective on the solar system and its galactic neighborhood. Later in the 18th and 19th century, as the development of telescopes and other technologies progressed, the size, content, and extent of the universe began to be questioned, as is illustrated in this slide, showing William Herschel's 1811 chart of his observation of nebula and distribution of them across the sky, and suggestions that they were something other than stars, along with Lord Ross's famous hand-drawn 1845 sketch of M51, the Whirlpool Nebula. These hints of a larger and more complex universe were suggested and further advanced later in the 19th century with the arrival of photography, as with Isaac Roberts' famous photo of Andromeda from 1888. Still, at the end of the 19th century, our view of the universe was somewhat parochial in nature. The accepted model of the universe at that time maintained that the Milky Way, or our home, was the universe. and that it was about 30,000 light years in diameter, with the solar system at the center. It further suggested that the common age of the Sun, the Milky Way, and the universe was some 20 to 40 million years, and that the mysterious spiral nebula that were then starting to be detected were other planetary systems emerging, just as our own solar system had. Points existed, but they were not mainstream until the first part of the 20th century, when a number of significant developments by individuals caused momentous changes in the way we understand the modern universe. This revolution in our concept of the cosmos, classified as the early modern, involved a number of significant steps over a 15-year period which combined to redefine the universe as we knew it. In 1912, Henrietta Leavitt's brilliant insight regarding the use of Cepheid variable stars as yardsticks or standard candles for measuring cosmological distances, coupled with Vesto Slipher's 1914 groundbreaking use of Doppler spectroscopy to discover that the recessional speeds of spiral nebula was many more times greater than that of any star, combined to give Edwin Hubble the tools that enabled him in 1925 to settle the 1920, quote, Great Debate, end of quote, by establishing definitively that the spiral nebula were in fact external island galaxies, and then by 1929 to proclaim that the universe was expanding as governed by what we now know as Hubble's law. All of this was put into a revolutionary new mathematical framework in 1915 by Albert Einstein with his general theory of relativity. Then in 1917, Einstein published a paper entitled, quote, The Cosmological Considerations of the General Theory of Relativity, end of quote, in which he attempted to mathematically describe a universe which was static, as that was the common assumption of the pre-Hubble era. He was forced to introduce a term in his equations called the cosmological constant, a fudge factor, if you will, to assure gravitational stability into his space-time. Einstein was challenged in this static universe assumption by several mathematician contemporaries. In 1927, an astronomer, mathematician, and priest named George Lemaitre reanalyzed Einstein's equations of general relativity without the static universe assumption and found that it matched the expansion as announced by Hubble several years later. In 1931, this forced Einstein to recant, embrace the expanding universe, and to admit that the cosmological constant was, quote, the biggest blunder of my life. As significant as Lemaitre's use of Einstein's mathematics to describe the dynamics of Hubble's expanding universe was his insight that this implied that in the past it must have been smaller, and further, that at some point there had to be a beginning or an origin, a primeval atom that had expanded to generate everything in today's universe. Lemaitre referred to this concept as, quote, the day without yesterday, end of quote. The expanding universe theory had been born, although it would be about 20 years later, in 1949, before British astronomer Fred Hoyle coined the name the Big Bang. He did it in a critical put down of Lemaitre's theory. Diane, this is about a 12-minute break here. If we're going to break, then I'd prefer to do it right now.
We're
do
good.
that?
We are good. That's why we front loaded the break so you could flow right through.
So we're going to keep going?
Keep going.
Okay. In spite of the acceptance of Einstein's mathematics as interpreted by Lemaitre's model, and verification by Hubble's measurements, the Big Bang theory did not immediately gain widespread acceptance in the astronomy community. Critics pointed out that using Hubble's data for expansion, the universe would only be 1.8 to 2 billion years old, much too young for the older stars, known to be up to about 10 billion years old, or even the geological age of the Earth. Others, conditioned to an eternal universe and cautious about potential religious overtones, had a difficult time accepting any notion of a creation date. Several alternative scenarios were proposed to account for Hubble's redshift measurements, but of these, only one received serious consideration over the ensuing decades. This was the steady state theory, as conceived of and championed by Fred Hoyle, with partners Thomas Gold and Herman Bondi in the mid-40s. Hoyle's theory, which described an eternal, ever-expanding, and continuously creating universe, would accommodate Hubble's law and an interpretation of Einstein's general relativity, along with some other observational evidences. Its long-term resiliency was evidenced by a survey conducted in 1959 by the Science Newsletter, which polled prominent astronomers as to their position on the theories. Of these experts, 33%, 24% preferred the steady state, and 29% were undecided or thought that both models were wrong. Among the early proponents of the Big Bang theory were many of the physics community who were busy exploring the revelations of the burgeoning field of nucleosynthesis. Einstein's most famous equation, E equals mc squared, had finally conceived a process for explaining the enormous energy produced by the sun and other stars. Developing the equations and conditions for transforming of hydrogen into helium led George Gamow and his associates to calculate the production ratio of these light elements under the conditions that would have existed in the Big Bang era. This ratio of 25 to 75% mass matched the measured ratio in today's universe, providing strong support for the Big Bang theory of cosmology. Gamow went further on to predict that there should be a remnant radiation field that might be detectable, and that it would have a signature redshifted microwave wavelength with a temperature of about 5 degrees Kelvin. This prediction, some 17 years before the cosmic microwave background radiation was first observed, was a monumental oversight that was due to the primitive status of microwave technology in 1948 and the inability of Gamow, Alpher, and Herman to convince their colleagues of its significance. They missed the Nobel Prize with that one. 50s and early 60s, the debate between the Big Bang and the steady state communities raged on. Revamping his eternal steady state universe theory and inadvertently solving a problem that had stymied the Big Bangers, when in 1957 he and his colleagues published a landmark paper called the B2FH, which was for Margaret and Jeffrey Burbidge, William Fowler, and then Fred Hoyle, which explained the synthesis of the heavier elements as products of stellar end-of-life explosions and processes, such as supernova, and not related to the birth of the universe. By this time, particle physics and quantum mechanics had become a serious partner of astronomy and integrated into cosmology. It would be 1965 when the next major chapter in the confirmation of the theory's acceptance by the scientific community occurred. As mentioned earlier, in 1948, George Gamow and company had predicted an artifact radiation from the Big Bang, which they called recombination. Their calculations had been based on the pressures, temperatures, and densities of the very early universe as prescribed by running the expanding universe clock backwards. They had predicted that about 300,000 years after the Big Bang, the temperature of the universe would have cooled to about 3,000 degrees Kelvin, which could have allowed the free electrons to combine with the nuclei, forming the first atoms, and would have emitted a sea of light, if you will, which still might be detectable. They had even predicted its microwave wavelength and frequency and calculated a redshift temperature measurement of about 5 degrees Kelvin today. In early 1964, Arno Penzias and Robert Wilson, two astronomers working for Bell Laboratory and preparing a large microwave antenna to do a sky survey of radio sources, were plagued by a persistent, unwanted background noise in their system that seemed to come from every direction. After months of effort to no avail to reduce or eliminate this noise, a casual exchange between Penzias and another astronomer at an astronomy conference led to one of the greatest discoveries in cosmological history. Further measurements and consultations confirmed that the noise problem that they had been struggling with for so long was indeed the cosmic background radiation which had been predicted by George Gamow some 17 years earlier as an essential part of the Big Bang, and not explainable by Hoyle's steady-state universe. Penzias and Wilson would be awarded the Nobel Prize for Physics in 1978 for their discovery. A further property of this baby picture of the universe was the expectation that if looked at in more detail, there might be fluctuations in the radiation that could reveal additional information about the early universe. Over a period of more than 2 decades, this effort was undertaken by many researchers, among them George Smoot. After many failures using high-altitude balloons and U-2 aircraft to minimize the effects of atmospheric water vapor, in 1992, Smoot was part of a team that was successful in using the COBE, or the COBE satellite, to confirm its uniformity across the sky and universe, but also to measure tiny temperature variations of 1 part in 100,000, 1 part in 100,000 or 1/100th of a thousandth degree in the cosmic microwave background radiation, which had major implications in our understanding of the early universe and its age, composition, and structure. For this analysis, Smoot was awarded the Nobel Prize in Physics in 2006. The importance of the accurate measurement of the cosmic microwave background was of such significance that several follow-up satellite missions have followed COBE, each of which have improved the resolution of the images and added further information to this ongoing primary contributor to the description of the Big Bang universe. Current measurements of the cosmic microwave background radiation are the most precisely measured spectrum in nature, with a redshifted temperature of 2.72548 plus or minus 57/100,000 degrees Kelvin above absolute zero, and fluctuations of 1/100,000th of a degree Kelvin, and an angular resolution of about 1/12th of a degree of arc. These measurements, combined with other measures and incorporated into other aspects of the analysis of the standard model of cosmology, such as particle physics and quantum mechanics and so on, and additional observations of galactic dynamics and content, finally secured the position of the Big Bang theory as the dominant description of the early universe amongst the astrophysics community. Some of the things it tells us is that our universe is 13.82 billion years old. and that it was initiated from a singularity which imprinted its signature some 379,000 years later as the cosmic microwave background radiation, when the universe had cooled to 3,000 degrees Kelvin, which allowed the so-called recombination of electrons to join the hydrogen-helium nuclei, plasma, to form the first atoms. This allowed light to radiate throughout the expanding universe for the first time. The pattern of the minute temperature variations in the cosmic microwave background radiation is believed to describe the structure of and the distribution of mass and energy in today's universe. Essentially, the cosmic microwave background radiation had ended the controversy between the steady state theories, but it had opened new controversies in the standard model of cosmology. The question of how fluctuations in space-time had generated the enormous disturbance, energy, and mass that had become the Big Bang universe from a singularity had by now become a mystery in the domain of particle physics and quantum mechanics, and some would say philosophy or religion, that continues to the present. Just as vexing was how this singularity expanded to become the cosmic background radiation detected as microwave signals some 13.78 billion years later. The cosmic microwave background radiation presents a photograph of the universe when it was 378,000 years old that we can look back to and make ever more deep of with sophisticated telescopes and instruments at various wavelengths, but it presents a barrier beyond which we cannot gather electromagnetic data. The timeline of events surrounding the Big Bang event, as currently postulated and accepted by the astrophysics community, are as follows. A quantum fluctuation in the balance of matter and antimatter in space-time occurred at the beginning, or the Big Bang itself, immediately followed by a period of time known as, quote, inflation, end of quote, lasting some 10 to the minus 35th seconds, during which the universe expanded some 10 to the 25th times, faster than the speed of light, during which the universe expanded some 10 to the 25th times, during which time it achieved a high degree of homogeneity. After this amazing expansion, the universe continued to expand at about the current Hubble rate for about 380,000 years to a radius of 42 million light years in radius, all the while cooling to a temperature of about 3,000 degrees Kelvin, at which temperature the first atoms formed and the universe became transparent and formed this baby picture of the universe that we now know as the cosmic microwave background radiation. In this scenario, by the way, at 1 second, when the universe was 1 second old, the theory says that it was 10 light years in diameter. They've been able to do this model to calculate those kind of numbers. From that inflation epoch or era, this expansion has continued now for some 13.8 billion years. That gives us the visible universe, and now spans some 93 billion light years, usually known as the observable universe. This description of the origin, history, and development of the universe was the accepted version toward the end of the 20th century. The inflation theory had its critics, but since it addressed basic issues with respect to the overall Big Bang theory and was based on sound particle physics and quantum mechanical principles, it was the mainstream thinking. However, other issues had arisen in the observational astronomy arena. The observed dynamics of galaxies and galaxy clusters were exhibiting unusual anomalies. They were not moving as Newton and Einstein had dictated. In 1980, an important paper by Vera Rubin and Kent Ford reviewed the results of 10 years of the observations of the rotation of galaxies, which revealed that the velocity of stars and hydrogen gas was fairly constant, as measured radially from the center, instead of dropping off as it should have, if governed by Kepler's law with the visible mass of the galaxy. Some invisible gravitational force was present. These graphs became known as Rubin's flat curves, and she spent much of her remaining career studying this phenomena. Previously, in 1933, this same effect had been observed by Fritz Zwicky when observing the Coma galaxy cluster, where to explain its motions gravitationally would require 400 times more mass than was visible. He called this missing mass Dunkel Materiae, or dark matter. Zwicky would never followed up on this discovery, but the term dark matter stuck, and Rubin's work with it would have a profound impact on cosmology going forward. Rubin's work revealed that most galaxies contain 5 to 6 times as much of this dark matter and its gravitational influence as visible matter. And this magnitude caused the cosmology community to take notice. Something big was out there that we couldn't see. Its mysterious property of not interacting with any electromagnetic radiation or light meant that direct observations were impossible. However, by using its gravitational effects by the early 1990s, dark matter's influence had been discovered throughout the universe in halos that surrounded galaxies and galaxy clusters. And using gravitational lensing and computing algorithms to map out dark matter, it was possible to visualize it, as is shown in this reconstruction, where the dark matter is shown as a light blue haze surrounding the visible elements of this galaxy cluster. Further refinements have resulted in spectacular images showing the collisions of galaxy clusters, including this spectacular view of the so-called bullet cluster, which clearly reveals how the ordinary matter, shown in pink, mostly gaseous in nature, reacts to the collision as opposed to the dark matter, which is shown in blue. More significantly, in 2007, the COSMOS series, the COSMOS survey, using images from a number of observatories, including the largest survey ever from the Hubble Space Telescope, 575 images and over 1,000 hours of observation with the Hubble, produced this three-dimensional map of dark matter clumping in an area of the sky 9 times that of the moon, which or some 5 times the volume of our home Virgo supercluster, where the Milky Way resides, and going back in time halfway to the Big Bang. This study indicates that normal matter accumulates along paths with the densest concentrations of dark matter, and that dark matter clumping probably provides the seeds for the formation of galaxies and galaxy clusters. Quantitative survey measurements calculated that fully 85% of the mass in the universe was made up of this stuff that we couldn't see. Dark matter was real. It was important. It exerted gravity, and we didn't know what it was. And this really got the attention of the particle physicists. And with the increase of the total mass of the universe by a whopping 85%, could the astronomers explain the effect on the expansion rate of the universe from this huge increase in its known gravity. By the mid-1980s, one thing was fairly certain about the expansion of the universe. It might have enough mass density to stop its expansion and recollapse it, which was called the Big Crunch. Or it might have so little density that it would never stop expanding, which is called the Big Chill. Gravity was certain to slow the expansion as time went on. Granted, the slowing had not been observed, but theoretically the universe is full of matter, and with the attractive force of gravity now multiplied times 6, it pulls all this matter together. By this time, there was a strong feeling by both the astronomy and the physics community in the need to better understand the expansion rate of the universe over the life of the universe. We needed to look back in time to see how the expansion rate had behaved when the universe was much younger. We needed to look much deeper in space. Recall that it was Edwin Hubble who in 1929 first measured and announced to the world that the universe was expanding. He accomplished this by measuring the distance and recessional velocities of 24 galaxies out to a distance of about 2 megaparsecs, or about 6.6 million light years, by using Henrietta Leavitt's Cepheus variable stars as, quote, standard candles for distance, and Vesto Slipher's Doppler redshift measurements for velocities. While Hubble's feat established the expanding universe and created Hubble's law and, quote, Hubble Constant, it was quite inaccurate and limited to the rather short cosmological distances for which Cepheid variable stars were observable, which is about 60 million light years. The inaccuracies were reduced by later observations and techniques, but the distance limitations imposed by the Cepheid visibility remained in place into the early 1990s. The Hubble constant, which is the slope of that distance versus the velocity plot, had become the standard for measuring the expansion of the universe and other related parameters. For example, the age of the universe is the reciprocal of the Hubble constant. As originally defined by Hubble, its value was about 500 kilometers per second per megaparseconds, which indicated a universe that was only 2 billion years old, younger than the age of the Earth. By 1990, when we could still barely measure distances outside of our own Virgo galaxy cluster, which is about 7.5 million light years, the Hubble constant had been revised down to somewhere between 50 and 100, which gave an age of the universe between 20 and 10 billion years, which is with still a great deal of uncertainty. With the precision satellite measurements of the cosmic microwave background radiation beginning in 1992 with the COBE mission that we talked about earlier, an independent method of dating the age of the universe and deriving the Hubble constant became available. Later, with the WMAP and the Planck satellite measurements in 2009, the Hubble constant value was inferred from the minute cosmic microwave background radiation temperature variations using assumptions about the amounts of dark matter, neutrinos, and other substances. And this calculated value, remember, it's calculated value of the Hubble constant, was within the tolerances of the direct observational values. But there was general agreement at this time, brought on by the discovery of dark matter, it was about time to pin down the value of the Hubble constant once and for all, and to see if it had changed in the last 13 billion years. Was a Hubble constant not constant? A new standard candle thus was needed, which was much brighter than the Cepheus used by Hubble and his successors. There was a general consensus that the best candidate for a Cepheid class standard candle that was visible over much brighter or greater distances would be supernova, except for two problems. Number one, they're very rare and unpredictable, and number two, their luminosity standardization was questionable. Supernova or supernovae are rare. They occur on the average about once a century in our galaxy, and their occurrence is not predictable. Fortunately, there are millions of galaxies out there to monitor. However, since a supernova event is transient, lasting only a couple of months, and unpredictable, detection, which can be accomplished with relatively modest telescopes, and then prompt follow-up measurements, which are required for more detailed measurements by larger telescopes, becomes a complex problem of managing the allocation of scarce technical resources, big telescopes, and observing time with short lead times and durations. In 1988, the National Science Foundation authorized $6 million for the establishment of the, quote, Center for Particle Astrophysics at the University of California in Berkeley, to recognize the connection of the very small with the very large in the physics versus astronomy world. The name of this agency might well have been the, quote, Center for Dark Matter, as this was the motivation for its creation. One of the first initiatives of this new organization was to create a group to look deeper into the universe, further into its past, and to try to see how much its expansion rate had been slowed down by gravity with the new dark matter. Remember, this is 1988. A small group of physicists and grad students at Berkeley's had been dabbling in the automated search and find system using a search and find supernova system using a 30-inch telescope near campus and a new computer technology, and by 1987 had bagged 4 supernova in nearby galaxies. This demonstration proved that their system could potentially automatically find more distant supernova in quantities given more resources. With the creation of this new Center for Particle Astrophysics, this small group was given the resources and a formal charge to measure the expansion rate of the early universe using supernova as a new standard candle. It was given a name, the Berkeley Automated Super Search, or Supernova Search. It was called the BASS team, B-A-S-S. It was given a formal assignment and expanded resources. Saul Perlmutter and his associates began their efforts to develop an automated system to identify and classify deep space supernovae and to validate a standard luminosity for them. By August of 1992, they had found their first deep space supernova with a record redshift indicating it to be from about 4.7 billion years ago. These physics guys had actually figured out how to do astronomy. They had developed what they called the batch method, whereby they would perform a wide field survey of a given region of the sky with as many as 100 observations over a couple of nights, encompassing tens of thousands of galaxies. Then 2.5 or 3 weeks later, they would resurvey the same region using a high-speed digital scanning search system, or as we used to call it, a computerized blink system. To compare each pair of photographs, they could quickly identify supernova candidates, which they could immediately send on to larger observatories, which had been scheduled ahead of time because they could deliver on supernova for detailed photometric and spectroscopic study. This method guaranteed them to find at least a few supernova in each batch. They could deliver supernovae on schedule. The second problem of luminosity standardization was at first a major problem in that the supernova 1As, that's a certain class of supernovae, which had been chosen as the most promising, and it had been chosen because it has a luminosity which allows distance measures some 500 times that of Cepheus. But it seemed to have an unacceptable variability in luminosity. This problem was solved in 1993 by an astronomer named Mark Phillips in an almost Henrietta Leavitt fashion. He had been studying the light curves of 9 nearby supernova 1As and noticed that the shallower the descending slope was, the brighter was the intrinsic luminosity. Thus, while supernova 1As did not have a standard luminosity, they could be calibrated. They could therefore be used as standard candles, bright enough to measure distances and velocities back to the earliest period of the universe. By this time, now we're in 1994, the astronomers had formed their own supernova search group, which was called the High Z team, or for high redshift. They were 6 years behind the physicists, but with hopes of catching up with their, quote, superior knowledge of supernova and all things astronomical, end of quote. The High Z team was comprised of more than a dozen astronomers from 7 observatories and institutions, and led by Brian Schmidt. Using their own version of the batch system and having access to a wide variety of telescopes, they quickly began bagging supernovae on their own. So, by the mid-1990s, there was a serious competition going on between the physics community, led by Saul Perlmutter, and the astronomers, led by Brian Schmidt, to discover how much the expansion of the universe was slowing down because of the huge increase of gravity from dark matter. By early 1996, the two teams were able to deliver supernovae on any scheduled date with the kind of confidence that allowed them to convince Robert Williams, who was the director of the Hubble Space Telescope Science Institute, who controls the Hubble, to use his discretionary time on the Hubble, which is like that which delivered the Hubble deep field images. Use the Hubble's high-resolution precision photometry and spectroscopy on a sampling of very deep space supernova to augment their growing database. In autumn of 1997, each team was busy analyzing their limited data sets, bolstered by several Hubble Space Telescope high-precision measurements. They were doing it in their own unique fashion, the physics team and the astronomy team, to find a preliminary answer as to how much the universe was slowing down due to its mass density. By the spring of 1998, each team was interested in reporting their findings as soon as possible in an effort to be first. Both teams reached a similar result almost simultaneously, but there was a problem. The data revealed that the expansion rate was not slowing down, as was presumed, but was increasing, suggesting that the increased mass density from dark matter was being canceled by some anti-gravity repulsive force. The physics team's analysis revealed that the mass density required to slow the expansion of the universe was now 30%. The astronomers' team's independent preliminary results came in a week later at 36%, too low density. These unexpected, amazing, and virtually identical results from two rival, competing, and completely independent scientific groups caused a major upheaval in cosmology that continues to the present. The preliminary conclusions have been reinforced and refined by much more data. The mysterious anti-gravity force has been given the name dark energy. And Saul Perlmutter and Brian Schmidt shared the 2011 Nobel Prize in Physics for its discovery, after a decade-long feud about who did it first. Dark energy, like dark matter, cannot be directly observed, but it can be inferred and therefore measured by its anti-gravitational effects on the visible large-scale matter in the universe. The new standard model of cosmology since 1998 postulates that the large-scale dynamics and expansion of the universe is controlled by a combination of gravity from matter, both regular and dark matter, and dark energy. The currently accepted values for this are about 5% regular matter, 27% dark matter, and 68% dark energy, which suggests that the expansion of the early universe was controlled by gravity and was slowing down until about 7 billion years ago, when dark energy's influence began to give us the accelerated expansion that we see today. And so, our knowledge of the universe, as we now understand it, or don't quite understand it, has evolved over the last 100 years through a series of significant steps, starting with Hubble, Einstein, and Lemaitre's expanding universe and the Big Bang Theory. Then came Gamow and Hoyle's postulation of the creation of the elements by marrying the laws of particle physics, quantum mechanics, to astronomical dynamics. The accidental discovery of the cosmic microwave background radiation, with its subsequent exquisite measurements allowing the detailed modeling of the birth of the universe. The science of astrophysics had come of age. Then came the last 50 years of major and in some ways speculative, confusing, and unexpected discoveries that have shaken the astrophysics world. First came Vera Rubin's documentation of a new source of gravitational influence which doesn't interact with light or radiation and dominates regular matter by a significant amount. We now call this material or quantity dark matter. Dark matter's presence created a new challenge to the astronomy and particle physics and together the astrophysics communities. Question was, how does all this dark matter affect the dynamics of the universe? The quest for that answer came to the question for the answer to that question became an interesting competition between the astronomy and physics community, which resulted in a minor revolution in astronomical measurement technology, but even more important, the discovery of yet another element in the control of the expansion of the universe. This time, the quantity was a repulsive force pervasive in the universe in amounts greater than that of all the gravitational attractive forces combined. We now call this entity dark energy. With the revelations from the cosmic microwave background radiation and the theory of inflation, and now dark matter and dark energy, the world of astrophysics has been revolutionized and is now in a significant state of flux. While our understanding of the universe, past, present, and future, is much advanced over what it was 100 or even 50 years ago, we now have a number of major questions which remain to be answered concerning this dark universe. Some of these questions are: 1. What is dark matter? It may be some as yet undiscovered subatomic particle or not. Since it doesn't react with electromagnetic radiation, we can't measure it directly. We have no idea what it is. Number 2, what is dark energy? It seems to be detectable only on very large scales, galactic or larger. It's repulsive, and that's about all we know about it. Number 3, is the Hubble constant a constant? And what is its true value? The accepted cosmic microwave background radiation calculated value of 67.4 is not consistent even with the tolerances with the directly measured value of 74. This gives us a 500 million difference in the age of the universe, from 13.8 to 13.3. Number 4, what is the mechanism for inflation? What field or force could have caused the faster than the speed of light expansion of the very early universe? Is there such a thing as an inflaton field? Number 5, is the universe homogeneous and isotropic on the largest scales? And finally, number 6, and probably most significant, what came before the Big Bang? These and many other questions are currently hot topics in today's study of the universe and are commanding worldwide efforts to resolve them. These questions are the justifications for billions of dollars being spent on programs like the LSST or Rubin Observatory or the James Webb Space Telescope. To quote the title of one of the books I mentioned earlier, the answer to these questions is, quote, we have no idea, but perhaps we soon will. I'd now like to conclude by quoting some closing remarks from a 2016 book I read by Stuart Clark, one of the ones I quoted earlier. It's entitled The Unknown Universe, one of my references. I just caution you, by the way, if any of you are planning on reading up on these things, make sure you check the copyright date on it, because books that were written more than 20 years ago are probably not relevant. But the quote from this book, The Unknown Universe, went on to say, quote, today, all of our wishes could be granted if we could directly detect dark matter and dark energy, end of quote. Secondly, quote, there are only 2 possibilities. Either dark matter and dark energy are real, and these vast reservoirs of matter and energy are just waiting to be found, or we have to radically rethink fundamental physics, end of quote. And finally, quote, either way, we live in an unknown universe, end of quote. And I would add further, we live in an exciting time for cosmology. And I'd finally like to now add another verse to a Don McLean song that I first rewrote in 2008 for a presentation entitled Astronomic Metrics, and then added a new verse in 2011 for the presentation of The Way We Found the Universe. Here is my finale version of Starry, Starry Night. If you'd like. Starry night, contemplate stuff about the Milky Way, thinking it's so far away that it's impossible to comprehend. Upon the thought that galaxy I'm from so far, we do not see them as they are, as they were. So that we try to understand the vastness of the universe. With measurements we sometimes curse. Was it so hard for us to know how distant is the feeble light? The starry, starry night. So long ago, astronomers tried to explain the theory modern eyes, and instruments that measure ground. They solve the mystery to Hubble came along and found that blinking star to stay. Andromeda was far away, much farther than the Milky Way. That Cepheus is blinking still. Yes, it always will. Now here's the finale. The starry night, contemplate starts with a gigantic burst of energy. Came to be from a singularity, expansion that today we see, cosmic radiation everywhere, dark mass and energy are cosmic things we cannot see, which constitutes mystery that we continue to explore. That universe has secrets still. I guess it always will. Thank you all. Questions? I don't know if we have time.
Since we're not getting kicked out of a lecture hall, I think we have time for a couple questions. Let's have it run until 9:40 at least. Going once, going twice. Come on, people. You can throw them in the chat too.
I have one thing, Jim. That was the best presentation that I think I've ever heard. It was just spectacular. Great job. Really, really great. I have one question for you. When it had to do with them discovering that the acceleration of the universe was going, how much did you happen to pick up on the fact that maybe it isn't quite that old because of the acceleration factor, and it actually being less time now since the beginning because of the acceleration, which they said had been going on for quite a while? Did you read anything about that?
Oh yeah, that's what this whole argument is about. Is trying to discover whether the Hubble constant is constant, and what the history of the universe's expansion is all about. You can't see anything beyond the cosmic microwave background radiation. That is a barrier beyond which we'll never be able to look. So they've got these particle physics and quantum mechanic models that are based on those kind of principles that describe what happened with the Big Bang itself and with this inflation period, which lasted only a fraction of a second, where the universe expanded to the point 380,000 years later, when we see the cosmic microwave radiation. But other than that, they're just trying to, every time they look back at one of these supernova, they've got another data point. And that's what this LSST telescope complex and some of the other new technology coming on is all about. They expect to have thousands and thousands of these supernova measurements with the redshift and with the brightness measurements for distance in the near future, where they'll have much better data to base their decisions on, or their evaluations on.
So the data could in fact be, the data they're finding out could in fact lessen the age, is what you're saying.
Yes, it could, but I think they're pretty confident in their current estimates that it's 13.78 roughly 13.78 billion years old.
Okay, thanks.
I have a comment. There may be a way to look back farther than the recombination era.
Okay.
With an age of 300,000 or 400,000 years. There are two ways. One is and neither of them is going to be easy. But this is not about easy, right? So
no
one
kidding.
of them is with neutrinos, which are extremely penetrating, and could have penetrated through the very dense universe earlier than an age of 300,000 years. The problem there is it's difficult to detect them, but methods are improving. The other way is with gravitational waves. The Europeans are leading the development of a much bigger gravitational wave detection system. Instead of the LIGO that's like 4 kilometers long for the light paths to measure gravitational waves, we're talking about putting satellites in space and that are like 1 million kilometers apart and measuring fluctuations in the distance between them. And they are saying that with that instrument, they may possibly be able to detect the bang, the vibration from the Big Bang event. So we might, with enormous difficulty, be able to look back farther than the cosmic microwave background radiation can let us see. Maybe.
Okay, you're reading something that's more recent than I've been able to pick up in all the books and stuff. But you're right. This is a very volatile issue. The whole astrophysics world. If you were a young man, that'd be a great field to get started in. Hey, Jonathan.
Yes, sir.
Can you? I'm still connected to you guys, but I can't seem to get back to the screen to see you.
Oh, let's see.
You can do about that. I can hear you, but I can't see you.
Take your step. Go down to the bottom. Go down to the bottom of the thing where it says. It'll say no near the top. It'll say.
Oh, there you are.
Yeah, I think I kicked you out of presenter role.
Yeah, there you go.
Okay. All right. Thanks.
Hey, Jonathan, go get him.
Any other questions? Hey, by the way, this is if you're interested at all in stuff like this, there's some great reading, and it's very interesting stuff. And there's a lot of stuff online, of course.
Did you find anything interesting about the Hoyle crew, including like Chip Arp, and did you sort of read into? Because I believe pretty much the steady state people are down to 3 or 4 tenured professors at this point.
You mean diehards?
Yeah.
Yeah. Well, Margaret Burbridge, who is on that famous report, she just died recently, last month, I believe. So, yeah. No, that's part of the fascination of the subject is some of the characters that were involved with this whole thing. Fritz Zwicky, for example, Ken.
Yeah. Fritz Zwicky, yes.
He really missed the boat in not jumping on the dark matter stuff 17 years before Vera Rubin did.
Wait, Jim, it's George Gamow, believe it or not. It's Gamow, but it's pronounced Gamoff, believe it or not. How's that for
Really,
trivia?
really. Learn something new every day.
Isn't that something? It's trivia. That's
So I was just going to make a couple of comments on the Great Courses Plus. I don't know if anybody else subscribes to that. Dr. Sean Carroll from Caltech has a lecture series called Dark Matter, Dark Energy, The Dark Side of the Universe. And it talks a lot about the stuff that you covered already, Jim. But there was one little thing that I thought was interesting was they talked about all the things that dark matter could not possibly be. So it's like, how did you rule out that it wasn't just dust or gas or something? And so there's a whole thing that goes on why it could not possibly be those things. But they do talk about the massive particles interact gravitationally. Interact gravitationally, but not electromagnetically, and sometimes referred to as WIMPs. The interesting comment that he made was that to detect one of these in a particle accelerator would require a particle accelerator with substantially more energy because it's a more massive particle, so you need more energy to accelerate it to near the speed of light so we can do the smashing of it. And he said, and we're literally at a point where we just can't afford to discover such a particle. So they don't. He's not saying that there are no more particles to discover. He's like, we've discovered everything we can afford to discover for now.
Well, this thing about the Higgs boson here last year, you recall, there were big hopes pinned on that, but that didn't pan out either. So remember the Higgs boson when they announced the discovery of that?
Oh yeah.
Yeah. Anyhow, it's a very, very fascinating subject. I thought one of the one of my things that caught my attention early was the fact that the physicists and the astronomers were competing with each other at that point for about 7 or 8 years. The physicists were trying to show the astronomers how to do astronomy, and the astronomers were trying to show them that they could do it better, and they both came up with the same unexpected conclusion.
How about that?
That's what surprised, and at about the same time, within a week, they each announced the discovery of, or the results of 6 or 7 years of investigations on completely different analytical methods, and they both came up with the same unexpected result, which resulted in dark energy, the conclusion of dark energy.
Cool.
All right. Well, 9:46. It was quite an evening. Thank you so much, Jim, for a
thank you.
incredible ride through the universe.
Great presentation.
And we will see you all in 3 short days.
3 short days.
The Cohen meeting.
By the way, Diane.
Yes.
Just a comment. A week from now, I'm going to have major back surgery, and I may be out of communication for a month or so.
Oh boy, good luck with that.
No, it's nothing critical. It's just I'm trying to correct the situation. So,
well, that's
still good luck with that.
If you don't hear from me online or anything, that'll be what.
Well, let us know, damn it.
Yes.
Yeah,
please. ATB. But more important than that, we just need you healthy in general.
Yeah, that's what we need.
So
right.
Let us know.
Right.
Thank you.
Agreed.
All right.
Anybody know, besides me watching the new Netflix series called Away?
Nope.
What's it called?
We're
Away,
really bad.
AWAY, about a woman astronaut going to Mars for 3 years. Hillary Swank.
Something to check out.
It's good. It's very unrealistic, but a good story nevertheless.
Okay.
On Netflix, streaming on Netflix.
Materials to help me fall asleep are good. So far, I'm studying David Butler's view of astronomy, and we're in the Virgo supercluster. So that's getting me to sleep these days.
I love it.
So, all right. Bid you all adieu. See you in 3 days.
3 days.
It was an excellent meeting.
Good night.
Yes, it was. Great presentation.
See you later.
Thanks,
Good
Jim.
night, all.
Thank you, Jim.
Good night.
Night, everyone. See you.
Good night, everybody.
Good night.